Okay, so quantum teleportation might sound too exciting and too science fiction-y to be of any actual interest technically, but it's actually a very fundamental primitive in computation. And so in this video, I'll say in a few minutes, I'll give you a little sketch of how teleportation gets used in computation. This might be a little more advanced, but it's really a pointer into the literature for those of you who are interested. Okay, so let's look at how teleportation proceeds. Right, so Alice has a qubit which is in the state, let's say she has this qubit which is in the state alpha 0 plus beta 1. It's in an unknown state. And then Alice wants to send this qubit over to Bob. And all they have is an entangled pair of qubits which they share, a Bell state. And so the teleportation is a protocol where Alice measures her two qubits in some appropriate basis, sends the two classical bits across to Bob, who makes some unitary correction to his qubit, and the qubit that Alice destroyed by making a measurement magically appears on Bob's side. Okay, so that's teleportation. Now, let's step back and think about it for a moment. So, what is it that, what determined, what basis the qubit psi reappeared on Bob's side? Well, if you think about it for a little while, you'll realize that what determined the basis was the fact that the Bell state happened to be of the form 0, 0 plus 1, 1. What if you had used 0, 1 plus 1, 0? Then if Alice's qubit had been a 0, it would have appeared on Bob's side as a 1, and vice versa. So now, why not take this a step further? Why not take Bob's qubit and apply a unitary rotation to it? You could apply any arbitrary unitary rotation to it. And now, when Alice does her teleportation step, wouldn't you expect it to arrive on Bob's side in this rotated basis? But if that were the case, then what you would have managed is, if Alice wanted to apply some unitary rotation to her qubit, it would appear on Bob's side pre-rotated. Okay, but then you could say, well, what's the point of doing something like this? After all, what does it matter? Alice applies the unitary rotation, the gate. Bob applies the gate. You have to apply it anyway. So here's the interesting part. The interesting part is that what this says is that you could apply a rotation, you could apply the gate before even touching the qubit. So in other words, suppose that our computation is unreliable. Suppose we don't quite have a handle on it. Sometimes it works, sometimes it doesn't. And on the other hand, the qubit that we want to apply the computation to, that's valuable. If we were to spoil it and have to make it all over again, that would take a lot of effort to create. What we could do is apply the gate in advance. We'd apply it to Bob's qubit in this Bell state. And if we spoil that computation, we could just discard that Bell state and start all over again with a new, fresh Bell state. And we could keep trying until we succeed in doing that rotation to our satisfaction. Once we are done with doing the rotation to our satisfaction, then we do a teleportation protocol, and lo and behold, the qubit reappears on Bob's side, properly rotated. Okay, that's the idea, at least, behind computation by teleportation. Okay, but to really make it happen, we need to do something a little more interesting. Okay, so this is our schematic of what we would like to happen. So we are trying to do teleportation. Before we even start the teleportation circuit, we apply a single qubit unitary U, a quantum gate U, to Bob's qubit. And then once we are satisfied we've managed to apply it, we want to teleport psi to Bob, and what we are expecting is Bob receives u times psi. Okay, so let's see whether this is going to work out as expected. Okay, so what happens? Well, here's the actual teleportation circuit. Remember what Alice does is she does a C0 from into her part of the Bell state. Then she does a Bell basis measurement, which is she applies a Hadamard here, measures these two qubits, calls up Bob, who applies either a X or a Z correction or both. Okay, so now what are we planning to do instead? Now what we've done is, before any of this teleportation circuit started, what we are doing is we are applying U to Bob's qubit. And what would we like to happen? Right? What actually have we managed to do? Well, what was supposed to happen was, without the U here, it's after we applied the X and Z corrections that we got psi. Meaning whatever the state was, let's say we only had to apply the X correction. So it was after applying the X correction, we got the correct bit psi, and having applied X, we then wanted to apply U to it, right? So if we applied this operator U followed by X, then we got the correct output. This created the output would be equal to U times psi, which is what we wanted. What do we actually end up applying? Well, we end up applying U first and then X. Okay. Now, in general, you know that matrices don't commute. And so U followed by X is, in general, not going to be equal to X followed by U. And so what we would have to do in order to actually do computation by teleportation is we'd actually have to apply some sort of correction after having done this. So we applied our gate too soon. We applied U and then X instead of X and then U. Okay, so it turns out that there are certain kinds of single qubit gates which actually commute with X. So you can apply them in any order. For these kinds of gates, it's actually very good. For simple gates, we might actually have equality here, and then those gates we can just do simply by teleportation. But there are other gates where they don't commute, but you can apply a very simple unitary correction. So you do get equality if you apply some unitary correction A. And if A is simple enough, then this is a worthwhile process to carry out. And this is what computation by teleportation does. So if you want to read more about this, here's the paper that introduced this concept. It's, I think, a very beautiful paper, and there are lots of follow-up works based on it, having to do with how you carry out quantum computation reliably in the presence of noise. So this is called fault-tolerant quantum computing. There are ways of using, what this also shows is that entanglement can be used as a resource in quantum computation. And then there's, this has been developed in very interesting ways in what's called quantum computation by measurement.